to the axis of rotation. Okay? So here's a case where this is x-axis and there's a curve. Usually we're dealing with this thing with a curve y equals f of x. Not this one. You can look at it this way, but if you rotate around x-axis, that your cone is slightly disoriented. So we are actually, axis of rotation is x-axis, not just like that wooden object. Its axis of rotation is x-axis. So here is the A and here's the B. And this is the region we're about to rotate. This is completely on the one side of this axis of rotation, right? And is this region attached to the axis of rotation? Correct? So that's the case, just like the cone. All right? So I'm going to give you a little picture and show you the little picture to understand this one better. Here they call this a disk method, but solid revolution I think is a better word. All right, here's an example. Right, here is the axis of rotation x, and here's the region underneath the curve between A and B. Region is attached to axis of rotation. Is that right? Okay, so I'm going to rotate it here. All right, it's acting slow. All right, if I go about like this, that side, let me show you the solid as well. You see that picture there? That was the side, and if I rotate it really quickly, and it is so quick, so your retina receive this everything as a one shot like that. So, but it's now complete one rotation, but that's the solid of rotation it's creating there, right? Make sense? So that's that, and I'm showing the next picture. I'm just going to sketch it. So actually I had it planned it here. If you think about one thing here. Well, I'll give you a picture of this one. If you rotate it around x-axis, and then you see that this side and this length and that length is going to be this end part in here. Pretty much the same size in the end part in there. Is that right? That side, if you look at the end part. And this curve will show up nicely, something like that there. And because of the rotation, it's going to be symmetric shape, nicely like that. And you just have to add, at the end, kind of add this perspective shape of a circle to that side. This is the end part in here. Is that right? And the other side, and there's end part. And it's a solid. And here's axis of cross section. So if you cut it right here, I'm going to use it red color, and then this shape here is perfect disk because it's solid rotation, right? So it's location x coordinate there, and if you turn this around, and that's going to be a perfect disk like this. And all you want to know is this radius r, right? Then it's a pi r squared. Then you write that down. So that point, let me draw it like this. Point in here is this vertical. Everywhere the radius is the same. So that line here is right here. That is the radius right there. Don't you think? Look at that. That line segment, I'm going to call P and Q here. That P goes there and Q goes there. That is rotated around. So this segment is actually rotated around the x-axis, creating a disk. Does that make sense? Look at it that way. So at the location, at x coordinate here, what is this r? Given x, what is this r? And then you can write down area. So here's a pi r. So area here is ax. What is ax in terms of r? Pi r squared, right? The whole area of the disk. And the goal here is what is r? So what do you think? R is the length of this one. So the top coordinate, f of x, right? Bottom coordinate, 0, because it's attached to the area. So ax here is pi times f of x, that r squared, right? What if this region was actually below the x-axis? There's one side, but it's below the x-axis, and the length will be negative f of x, don't you think? But it's going to be squared anyway. Pi times f. So this actually holds for both cases, the region being up there, region being down there. It doesn't matter. You'll be squaring it anyway. So if it is in that formulation, the volume of this one is from A to B of cross-section area, which is pi times r squared. R is the segment in here, and f of x squared into x. Since this formula is introduced, you have a tendency to just memorize it. Try to do the problem too mechanically. Maybe you have to do it to some degree like that in the test, but you know that doesn't really help you to understand this mathematical part and geometry part. So try to understand how this formula has come about. It's a cross-sectional area. Cross-section is a area of a disk. It's pi r squared. That makes perfect sense. That f of x right there is the radius. So that's the formula. Okay? We looked at the cone. You might remember the area of a cone. I mean the volume of a cone. But you can use this formula to compute the volume of a cone, right? Okay? So why don't we make that an exercise in here? Today's exercise number 1. I'll give you a setup. Here's x-axis. You know, translation and shifting to the left and right is not going to change the volume, right? But you have to keep the situation that region is attached to the x-axis. So you're not going to shift up and down. You're going to keep it this way. Other than that, you have to move your axis of rotation as well. So don't put anywhere else. Just simply like this. If you rotate this one like that, axis of rotation of x, then you believe you're going to generate a cone. Is that right? So I'm going to call that capital R down there. Do you see that capital R here is going to be the radius of a bottom base of a cone? Is that right? If you rotate it, do you see that? And that length h here is going to be the height of a cone. But its cone is that like that wooden object in that, you know, in that tool, it's slanted like the sideway cone, right? So compute the volume of this cone is a question. So let's look at, you need the formula of y equals, you know, that's the formula you need to have, right? It's a line, right? So what kind of line is that? I'm giving you all this right now. What is the slope? R and H give you a clear idea about the slope of this object, right? R divided by H? Right. Not quite. R and H are really the positive number right now, but you see that's a negative slope, right? So you have to put a negative there. Correct? X plus y-intercept, right? Slope times x plus y-intercept. What is the y-intercept here? I think it's R, right? Y-intercept R. So the formula of that line, that straight line, the slope negative R over H, rise over run, x plus y-intercept R. So we have the formula. So we're in this setting. We have y equals x going from 0 to h. You see that? And you stick it in here. And that's the formula. But I want you to have this habit, like before, even in the area between regions and the volume of cross-section, always draw this vertical line. This is the line that is actually being rotated, and that must be the radius of the rotation. Okay? And then you use this formula. Okay, so that's your exercise. Stick this thing into this formula in here. Compute the integral, where capital R and H are all constants, right? All constants. Right, you'll arrive at least this much of formulation. 0 to pi and pi times whatever this y equals f of x formula is taken there, right? And you know this is not something difficult. You have to square it and tedious like that, right? And let me show you how to handle the rest of the part quickly. You will have some sort of problem like this where the parameters involved in here, constant involved given a letter, so you have more difficulty of actually computing this one into simplified form. So remember, this is really the linear, right? This whole thing is linear. And when you make a substitution, the integral gets a lot easier in the linear case. And this r is a common factor, is that right? So I can pull that out. If you pull that out, and pi is also a common factor. If I pull out r under squared, right? And that's going to be r squared, correct? R is pulled out, under squared is r squared. From 0 to h, r is pulled out 1 minus x 1 over h times x dx and squared. That's what you have to integrate, right? Think about it. If this is 1 minus 1 over 7 times x squared, if you make a substitution, because it's linear, its derivative is constant, it's going to cause no problem. So we're going to make a substitution. U equals what? Easiest way to substitute here. U is going to be what? If this were 1 minus 1/7 times x, that whole 1 minus 1/7 times x will be my x, or my u. So what is du dx? Negative 1 over h, is that right? Negative 1 over h, that's the. And then we multiply reciprocal of this one when you switch it, right? So let's do that. Pi times r squared. And this is going to be u value, right? Correct? What is u when x equals 0? Here's a U-Substitution formula right there. When x equals 0? 1. What about u value when x equals h? X equals 0. So you can see that it turns to a pretty nice number there, right? 1, 0. And what about here? U squared. The whole thing is just u there now, right? And what do we multiply? Reciprocal of du dx, right? What is reciprocal of du dx? Du dx is calculated here for you. Reciprocal is negative h, right? So times negative h. Du. That is my substitution rule. Okay? Change in terms of u and multiply the reciprocal of du dx. Straightforward. All right. Use, what are you going to do with this negative and then looking at 1 is down there and 0 is up there? You can flip it, right? Pi r squared times h, and you can flip it back to 0 to 1 using the negative, and then you go back to u squared du, right? Cool? All right, so who can do this in your head? Antiderivative of u squared, the definite integral u squared from 0 to 1. That's a 1/3. I think that's a 1/3. So it's a 1/3. Let me organize like this. Pi times r squared, because I remember something about pi times r squared times h. What was the pi times r squared, you think? The cone now looked like this, right? What is the meaning of pi times r squared that showed up in our formula? Area of the base, right? Times h, the height of a cone, times its universal factor, 1/3. Right? So even if the cone is over here, can you imagine that there's something wrong in the factory? They generated cone slightly tilted like this. So the perpendicular line from the top of the cone down there is not in the center, slightly tilted. Okay? And that has still had h and the altitude there, and the base is there, r there. And this one is still the same. Pi times, 1/3 times the pi r squared base times height. 1/3 is always there. They actually, back then in the ancient time, they put it in the water and measure the difference of they realized it's always 1/3. This mysterious number, always 1/3, is involved. Any cone shape. Now, trained in modern mathematicians and students, and somebody asking, where's this 1/3 coming from? Integral of u squared. Integral of u squared is responsible for that 1/3 in the actual analysis, right? If somebody, this is actually introduced in an early stage and everybody's education, where is this 1/3 coming from? And then there's an actually sophisticated answer to that. It is because of this factor right there. And no matter what setting, this will show up after you change your variable. You have to do the substitution rule. This integral of 0 to 1 of u squared. So short answer is a calculation of the volume of a cone. If you reset the change of substitution rule nicely, there's always this factor of integral of 0 to 1 of u squared that is responsible for 1/3. Okay? All right, R is the region bounded by the curve f of x equals x plus 1 squared by x-axis and the line x equals 0 and x equals 2. And find the volume of a solid, of the revolution obtained by this region about x-axis. So that's going to be our exercise number 2. Exercise number 1 was a cone thing, right? But let's check on the picture first. And everybody will work on the first part with drawing the picture, the region, right? Before you rotate it. And let's do that part first. And once everybody agree on that region, and we're going to do this volume of this rotation. So exercise 2, part 1, sketch the region correctly. All right, the curve y equals x plus 1 squared is a shift of y equals x squared to the left by 1, right? Remember that principle of shifting? If you're looking at x plus 1, it's actually -1 horizontal unit. So y equals x squared, the vortex in the 0, 0 is shifted to the left by 1 unit, so it's -1. And they are putting 0 and 2, that's vertical line, so that's the region they're talking about. And I use the vertical shades because that is actually the radius being rotated around the x-axis in here. So also, I'm indicating here with that circular arrow, its axis of rotation. Can you imagine the shape of this rotation? Like a cone-shaped, truncated cone, but the side is not flat, but it's kind of, curved around like this, right? Make sense? All right, that's the region. So I want you to enter the volume formula. Write down the typical volume formula. V equals integral of where to where, and what's inside that? Area of the disk, an intermediate circular section, cross section, right? Well, let's at least look at this first formulation. Think about integrating later. A volume is from 0 to 2, right? Pi times f of x squared. F of x is already squared there, so it's going to be 4th power. Okay, that's a formulation. And actually, how to calculate this is just integration technique. But I hope you see the power of a chain rule here, how that makes it actually everything convenient, rather than expanding this one 4th power 4 times versus, all right, it's a linear. Anytime it's a linear there, it's a good idea to change it into simpler u value, and then integral is going to be simpler. All right? So with that substitution, it's just quick like that. Any question about this problem? Good? All right, let me give you one more formulation that is not case 1. It is just same. It's still case 1. That's not case 2. It's still case 1, but it's a different orientation. So here, any question about example 2? Is that all right? So let's look at this formulation here. Y-axis, and how about this guy here? That's the region. Think about the way I shaded this one. Before I vertically shaded the region, this time horizontally, and this is y equals a and y equals b going up there. And we're rotating around which axis? Y-axis, right? Okay, think about this one. Here's a point P here and point Q. That's going to serve as a rotation radius being rotated here like that. Do you need to know x coordinates of this thing or y coordinates of this thing, P and Q, to compute the area of a disk that is obtained by rotating the segment P and Q. Do you need x coordinate or y coordinate? X coordinate, right? X coordinate of this one horizontally move, so x coordinate of the other one. So you want this formula in being this form. I want x coordinate whatever, right? So that is in between, written in terms of g of y. Given y coordinate in there, what is the x coordinate of that horizontal line? So you want to formulate it like this. X coordinate equals in terms of y coordinate. Make sense? So let's formulate in this case. V, the volume of this one, is going from where to where? Each of this line segment in circular section, y coordinate going from A to B, right? And what is the area of the section? Pi times radius of PQ here. The gy minus that is just gy. Is that right? N squared. That gy is really measuring this PQ, or negative gy is correct if this side is actually on the other side, but squaring it, it's going to end up at the same formula, so dy. Does that make sense? All right. So vertical, the axis of rotation cross section is x, therefore y equals in terms of x, and here it's rotated around the vertical axis like this, then your main variable is y, and then this boundary curve must be x equal in the form of x equals something in terms of y. All right, maybe with actual example this will make more sense. So let me find a good example. Third exercise problem, we look at this region attached to the y-axis, an axis of rotations y, and what is the volume? I think it's this cone, like this. As you rotate around like that, compute the volume. So draw this line the way I shaded it. That really helps you to figure out, is that supposed to be in terms of x and y? Things like that, it really helps you. All right, was that okay? So try to have that habit. It begin to get can confuse and more because of this orientation. And if you know you're integrating with respect to y, then everything has to be in terms of y, right? You can stick it in there x and then differentiate with respect to x. That gives you kind of clue that it has to be written for solve for x or y. Austin, do you have a question? All right, here is case 2. The case 1 was the region that is attached to the x-axis, the axis of rotation, right? So let's write that down just to summarize it first. Case 1 was region attached to axis of rotation, right? And the formula was the volume going from A to B of whatever the variable, the dt, could be x or y, right? And it has to be pi times f of t squared. T is the parameter for axis of rotation, could be x and y. Make sense? That's when it's attached. In case 2 is region detached, or not attached, not attached to the region, to the axis. So this student find this part a lot more confusing than the other, and I think I need to use that animation again. Hope this time it's going to work. I think it's called a watch method down there. Oh, y-axis is already there. Where's the animation? I think it's above here. All right, so you see that there's a 2 curve bounding this region. It is away from x-axis, right? Which is the axis of rotation. And here's this things be about rotated here, and we go about there, and solid is showing. So if you rotate it around there, Do you see that it's rotated around, and keeping this distance in between and here, it generates this this region in between that is kind of a hole in there. You see that from that picture? So if you do the cross section, I hope you can see the cross section there is not a complete disk. Let me get rid of that thing. I hope it still shows that disk. This is a cross section in there after you make complete rotation. So it's not a disk, but is a punctured disk, and there's a hole in there, right? So that's the cross section. So think about. So this general picture makes sense, right? So that's isn't that what you did for the donut yesterday when you did that? The cross section. I also loaded the picture. That's the area. So in general, if we have a region like this between A and B, and here is the vertical shade method again, and I'm focusing on this particular spot, P and Q. When you rotate it, it's going to generate cross section like this, where there's this P and Q right there, and it's perspective view. So if you rotate around nicely, that's going to be this and that. So let me keep this upward there still. That's the point P, and that's the point Q, but it is kind of different angle looking at, flipped around. All right? So that's the center, concentric center of both circle, and the radius out there is going to be R2, right? And radius inside is going to be R1. Okay? So how would you calculate the area in between this, ring? The Saturn ring. That's exactly what it looks like, right? How do you compute the area if you have R2 and R1 given? The outer disk minus outer inside disk, right? So let's see the area here. AX is becoming pi times R2 squared, right? What is pi times R2 squared? It's the area of the entire disk minus area of the inside disk, right? And that's the area. That is different from pi r minus r2 minus r1 squared. You see that these are not the same thing. You can't subtract first and square it, and you have to square first and subtract off. There's difference, right? This one measures that is rotate this one around P. That's what it is. But if you rotate around axis that is away from the region, then it has to be careful like this. And it's not the same thing as this one. I used to have a lot of wrong answer computed like this in the test. Okay? Alright, that's remember, if it is away from that axis, it looks like this. Area minus area makes it square minus square. Right? So we needed information. Let's say that was given by f of x out there, and this is given by y equals g of x out there. So we have one formula for the bottom part, one formula for the top part. So how this formula is going to go? V volume is A to B, right? And cross-sectional area, right? Can somebody like to volunteer for this? Area of the outer disk, right? What is that? Pi times f of x squared, thank you, minus pi times inside the square, g of x squared. This time, it matters. The order matters, right? Because you're subtracting. So if this region is described below the x-axis, then whatever is away from it have to go outside. Does that make sense? So this one is a more away, further. What is the word? Adjective. Further curve, further away curve. That makes sense to me. Curve or further away. From where? Outer curve. That's a better outer curve. Thank you. Outer curve and inner curve. They may sometimes cross around just like the area, right? And then you have to divide it up. Here is outer curve, inner curve, and outer curve, inner curve. With Mathematica, probably you can handle it, but by hand that will be a nightmare to calculate things like that, right? But that's important formulation. To instead of just up and down and outer and inner is a better word to describe what goes up first and later inside. Does that make sense? All right. Let's read this problem together. Regions bounded by root x and x squared between 0 and 1. And what is the volume of solid as the result of when the region R is revolved about the x-axis? This is exercise number 4. Is that right? Exercise number 4. We're going to sketch the region first. We're going to check on that all together and continue to the next part using that formula I just described. So I sketched the region in between these two curves, between 0 and 1, that happen to be the exactly intersection point. So there's no truncated side in the left end and right end. It just closes up like this nicely, right? 0 and 1. If you rotate it, you can imagine the shape, but that doesn't really help you actually compute the volume of it. Always think about the cross section. How does the cross section look like? You look at this vertical segment. This is rotated around, which is away from this line segment, x-axis there, and then you're going to create something like this as you rotate this around x-axis. Make sense? Yeah. So now that's the understanding of the shape, especially the cross section. That's what matters for computing the volume, not the actual three-dimensional figure. So go ahead and calculate the volume. All right, how was it? Outer curve, inner curve. That's a really good word to remember how the formula works, right? Okay, that relative term is better. So do you believe this one is perfectly symmetric around y equals x because one function is inverses to the other, right? So what if I go and rotate this one like that around y-axis instead of x-axis? Then because what you see over here and what you see over there is exactly the same because it's x squared and root x are inverses to each other. So you will expect you're going to get the same answer. But if there's a slightly different shape, if this is 2x squared, I'm keeping this root x, then you expect a different volume, right? Yeah. But let's go ahead and formulate it as an additional thing, also in exercise number 5. Go ahead and do that rotation around y-axis. Outer curve, inner curve, and see if you can formulate it. I don't think we did that. We only did that with the x-axis, but just use the principle and see if you can formulate it with respect to y. Volume of the solid revolved about y-axis this time. Think about the principle. The variable is y. Draw a horizontal segment because it's along the y, right? And think about what is outer curve, what is inner curve relative to axis of rotation. And with the outer curve, area of a disk. With the inner curve, area of a disk. And that's what you have to do. I think the line segment you're drawing is really helping you to checking, and then when you're even writing it down, so is this the right coordinate that I'm calculating and things like that. So that's why I stick to that. Also later, there's a slightly different, everything is really the cross section. Do you agree? I started this entire volume section with one theme, cross section, cross section, cross section. These are all about cross section, right? So axis of rotation and axis of cross section, things I'm sketching in the segment are always perpendicular to each other because of that. The next method, the shell method, is opposite. The axis of rotation and things that we're sketching is a parallel. So if you have this habit of sketching the segment, it really helps you to not get confused with that method that's coming later. All right? So all this is a cross-section method. It's perpendicular to the axis. All right. Is this exercise number 5 or something? Okay. Exercise number 6. Again, we're going to do sketching first. We're going to check on that and then do the volume. This time is region not attached to the axis of rotation, and rotation of axis is axis of rotation is y-axis. Sketch the region first. Or when you sketch this thing, it's solve for x. Switch around, sketch y equals x cubed, and flipped around y equals x. That's how it goes. So cube curve flipped around x equals x, y equals x, and x equals 4y. Sure, it's a line, so assuming that it's going to cross like that. That's just a picture, right? So we know it crosses at x equals 0, and probably we want to know what this guy is here. Let's say it's a b, right? Actually, that's not what I want to know. I want to know this guy here. What do you think? Because we're doing with respect to y. So use and just find that intersection point b out there, and compute the volume when it's rotated around x-axis. There is one part that's attached to that region, but overall it's not attached. Alright, was that okay? It was good. It's already solved for, that's why I circled that. It's already solved for x, right? The equation is already given in x equals y cubed and x equals 4y. Okay? We have 1 minute left, and let me show you this problem that you did last night. And here is x-axis. Alright, I got that over here. This is axis of revolution right here. And you're rotating this one here, okay? And if you're doing the cross-section method in here, and look at this curve, and if it is really that not arbitrary shape, it is actually looking like this, what do you think is the outer curve of this one in here? I think it's tricky. What is the outer curve? This is axis, right? This is axis. It's always about to the axis, draw this perpendicular line, PQ. Here's y, and here's a perpendicular line, right? If this whole thing is a perpendicular line, goes like this, right? Let me use this over here. This is the region. Isn't that the perpendicular line, PQ? That's going to be the ring it generates, right? But how about over here? That's something different. Do you see the difference? Of this Q point over there is using this vertical line, and over here using something else, right? So do you see that you have to split up the integral in 2 parts? If you're doing washer method, right, you have to use this formula, and in between here and here y value you have to use different formula. But it's possible, right? If you can write this one in terms of x equals something. It's possible. With mathematics, I'm sure we can compute it. So this method is different. It uses this different idea. We're rotating in here like this, but we're not drawing a rectangle. That PQ is really representing a rectangle or radius in there, right? So this time we're going to just do like this, which is parallel, right? That's difference. All the thing we're doing before is this PQ always perpendicular to the axis of rotation. This time it's a parallel to the axis of rotation. Is that right? So there's a very different method. So if you rotate around, that's the shape. And the next thing is that this picture I showed you. And if you rotate this little blue segment around this y, do you see that kind of this ring, thin can of this thing that is showing up? Does that make sense? Yeah, that's what you're going to have. So I'm going to sketch it over here. If you rotate this thing around, so that was going back to Riemann sum. This is fundamentally different method, therefore back to Riemann sum again, right? Okay, here's xk. Then you rotate that segment and actually approximate. You cut it here to look at this rectangle rotated around, and then what you're going to get is this going to exaggerate a little bit. Usually this is a very thin part, and this is a shell they created here. Inside there's a hole, and this hole is really big, so this thickness is very small. So if you have lots of other rectangles around it here and create this shell, do you see they never overlap? This is perfectly, you have, you know, different size of a cookie cutter that overlapping in here. That's exactly what this one is generating. If you have different rectangles going around and you have different sizes of this one, but they are not overlapping, they're just all stacked up and kind of creating this shape. So we're going to calculate the volume of this one and add them all up, and that's going to be the volume of the whole thing. And I hope you understand, again, it is different from cross-section. Think about the shape, and then this fundamental thing that we're rotating is parallel, not cross-section, perpendicular. All right, let's compute this one. This one has xk coordinate. Is that right? And inside it here, xk minus 1, right? So if I choose this right endpoint to get the height, and again, if you really rotate this actual thing, you're not going to have a flat top, right? But I just cut it, approximation here, right? So that's what you're calculating. So do you know the volume of outer can solid? Well, let's first think about the height. This height is important. If I write this function part, y equals f of x, sorry about this little disorganized part, y equals f of x. If you stick an xk in there, you see that's exactly f of xk. Does that make sense? If I have the formula for the curve, you stick in x equals something there, that'll give you the height. Okay? If this negative number, it's actually have to turn to a positive number, right? But let's say there's in the first quadrant, it looks like this. All right? What is the volume of a solid can? Base times height, right? Base times height. So this volume of this kth shell is going to be the can of the outer part minus the volume of the can of inside part, right? So what is the base area of the bigger shell, bigger can, solid? Base times height, what is the base? Circular, right? So pi r squared. What is r there? You see xk, that's the center in here, that's the rotation, that's where y-axis is. So that's the distance from here to there, right? That's the radius of the bottom bigger solid, correct? So the radius is the coordinate xk. So xk is over here, and that's the axis of rotation, that's the radius, that's this how it's go around. That's xk, that's the radius. Pi r squared, xk squared. That's the area of the base. What is the height? Height is this one. It's common for both can, right? So here's going to be f of xk. Fair enough? That's the volume of the bigger solid. Minus what? Pi times inner one. What is the radius of the smaller one? Right. So xk minus 1 squared will be the area of the bottom can there, right? So that's the inside part there. Xk minus 1. And it's also here, that part is xk minus 1. Positive, negative doesn't matter, we're going to be squared anyway. So there is f of xk, not xk minus 1. Was cut it, the height is common for that one. So this is the volume of vk. If you add them all up, that becomes what? The volume of entire rotation. Different way of looking at it. Okay? All right. Pi n f of xk is common, correct? Yeah, so delta vk is now xk. I'm going to keep the pi in front. Pi is there. Xk squared, xk minus 1 squared out there, f of xk is common. You factor it out like this. Make sense? Okay. So all you have to do now is to put the summation in front of it, right? And that's going to be the volume. But do you see that delta xk is missing in here? if you want this thing is going to be Riemann sum, you want delta xk in there. Is that right? But delta xk is not in there. So we want to have delta xk in there, put in the summation and enter Riemann sum, therefore you write it as integral. Does anybody see where the delta xk is hidden in here? How about that factoring part? Do you see how this xk star squared minus x minus k minus 1 squared factored? Like a squared minus b squared? Xk minus 1, xk, let me do xk plus 1. You know a squared minus, let me write down here, a squared minus b squared factors a minus b, a plus b. Is that right? So I'm going to write it like this, a plus b, a minus b. Same thing, xk minus 1, f of xk. That square part, difference of square part factors like this. Now, do you see delta x? Where is delta x? What is delta x? Delta x is this length in between those two, xk and xk minus 1. Is that right? Yeah. So do you see that? It's right here. That is delta xk. Now we pulled out delta xk, so put it to the other side and think about the other part. So difficulty in here is that we have this xk plus xk minus 1 and f of xk. Usually we put the delta xk all the way to the right side, so there it is. Problem is that it's not just xk, there's xk minus 1 showed up, right? This is already truncated version, so it's not really the same delta vk, although I'm using this equal symbol in here. And book usually, some book do it correctly and some book, I think our book is a little sloppy about this part. And enter in here, this xk and xk minus 1 is almost the same because it's very, very small, right? So why don't we replace that xk minus 1 with xk, then it becomes 2xk, right? Then it's not the same, it's just, there's a slight error in that it causes the worry that what's going to happen to the error if you add up so many terms. You've seen that example before, right? Lots of error can be some significant quantity. So it causes error, but it is a correct answer, but it is a completely wrong logic. And if you jump going like that. So the correct version goes like this. It gets a little more difficult, but it is really the right way to see this problem. There's already that xk squared minus xk minus squared. So I want you to look at this mean value theorem. It pulled out this very interesting trick and logic in there. Do you know what mean value theorem is? Mean value theorem goes like this. If you have a function f of x that is not that function, I'm going to use hx instead. Hx, and if you have 2 points, let's say b and a, and divided by b minus a, this is the slope of a secant line. It's a mean value. It's a average value and things like that. Do you know what happened to this one in terms of derivative? This becomes a derivative of some value in between in there. This interpretation really is simple. Here is a curve y equals hx, and here's a and b. And here is the meaning of, let me cut it through so that not get confused. Suppose it looks like this. And this is y equal hx, and is a and b. The meaning of hb minus ha is the height, this rise part, and b minus a is the run part, right? So this is the slope of this line cutting through these 2 points on the graph. What is h prime of c? Slope of a tangent line, right? Do you see anywhere on the point of this curve, slope of the tangent line is the same as the slope of the secant line? Can you locate that in between a and b? Kind of parallel slide this line so that you see that over there, somewhere in this line, seems like at that point C, the slope of the tangent line is going to be equal to the slope of that line, right? Seems like there exist points like that. So mean value theorem asserts the existence of that number, that derivative value actually equates that. That was the mean value theorem. And it's a really powerful theorem to take care of it, uniqueness and some of the theoretical result. And here at the same time, we're doing that. So we're going to apply hx being x squared, because x squared minus x squared, xk minus 1 squared, right? That seems like the top part there. If you apply that, you have, and this one, xk minus 1, xk in there, this is what you get. Top is at h of xk, so that's going to be hxk squared, xk minus 1 squared, divided by xk minus xk minus 1. That's the direct application of mean value theorem. And this interesting theorem asserts that its derivative, what is the derivative of this x squared? 2x, right? And 2x, and that's it. Somewhere in between xk minus 1 xk, there is a value, and this whole thing is equals the value of a derivative. Okay? So, but we don't know what that c is, right? So there is a nice notation in the context of Riemann sum, in between xk and xk minus 1. Remember that notation? xk star? Anywhere in between it was denoted by xk star. And integrability of Riemann's theorem says that it doesn't matter if you choose xk, xk minus 1, anything in the middle, they all go to integral f of x dx. So whatever that xk star is, this whole thing is equal to 2xk star. Correct? So if you solve for xk squared minus xk minus 1 squared, it becomes xk star times this xk minus xk minus 1. In the Riemann sum context, what is a better notation for that? Xk minus 1? Delta xk. That's right. So let me copy that down again. The volume of Vk of that thin cylinder was pi times xk squared minus xk minus 1 squared times f of x. Now mean value theorem gives some magic formulation of this thing, xk squared minus xk minus 1 squared, as a 2 times, the pi is still there, pi times a 2 times xk star times delta xk, and there was that f of xk out there. And you put that delta xk out there, then you have 2 pi xk star f of xk times the delta xk. All right, this f of xk has nothing to do with that xk squared and xk minus 1 squared computation. So at the beginning, if you replace it in truncated version in here, if you replace it with this xk star, and that's a better formulation than the earlier one. So redefine this one. 2 pi xk star with f of xk star delta xk. Now everything is in xk star, and there's a delta xk multiplied in there. So the entire volume, the Riemann sum, is k going from 1 through n of 2 pi xk star f of xk star delta xk. That is supposed to be very close to the volume of the original thing. If you now enter integral, it goes like this: integral from a to b. These are because we're integrating over x, these are the x values, right? This could be confusing with the rotation around y-axis. You used to integrate over y. So is x equals b. It's a 2 pi x f of x dx. So that's the formula. They arrive at here. So let me help you to understand the final formula, because this derivation is too confusing and convoluted, and this mean value theorem is really distracting and all that. Right, this is the idea. So what is the meaning of this 2 pi x f of x? All right. When we enter this limit, the thickness of the can becomes almost 0. So maybe I can sketch it like this. It's really, really thin, and I hope this vertical line gives you an idea. It was just a thin slice wrapped around, right? So and then this distance in here is x. Does anybody remember the meaning of 2 pi x? That's the circumference, right? That's circumference. So that 2 pi x is the circumference of the bottom. F of x was the height. Remember that? So what does that represent? 2 pi x, bottom circumference, times f of x. And this whole thing represents, therefore, area of the side of a shell. That's what they call the shell. Area of the side of the kth shell, pretty much. Okay? So if you integrate area, you end up at usually volume. Remember, cross-sectional area, you integrate it, you end up at volume. So same analysis here, but it is not the same thing, not the cross-sectional area. So you can't just, hey, here's the collection of areas, I can just put integral to get the volume. It's not that simple. It doesn't work always like that. You have to go through a little bit of careful analysis to understand your stripping off analysis is actually okay. And there's some careful analysis I have to go through. All right. But it's still, as far as concerned, we analyze it this way, and it seems like a very different computation. Is that really going to be the same as a cross-sectional method in here? Answer is yes, and there's a way to prove it, and which we're not going to do in here right now. But that's the formula. So let me summarize it here again. Here's y-axis. Here's some region, maybe I can exaggerate a little bit more. Here like that. Especially if there's an up and down like this, and if you're rotating around y-axis, the cross-sectional method is difficult. Cross-sectional method, if it is a y-axis, you have to do a perpendicular line. You can see when you do the perpendicular line, you have to group lots of different segments, right? So that's going to be ugly. So this is more powerful because this is x integral. So if you put x in there, the line you have to draw is a parallel to, if it is shell method, a parallel to the axis of rotation. So here is the line. As you can see, if you put any line in there, if you have a formula y equals f of x, there's no difficulty. Getting this f of x in there is always easy if you're just given by one formula, right? So that is f of x in there. That goes there, and this is a, and that's b. There's nothing else. It's 2 pi x is just exactly the same thing. Does that make sense? So let me give you another interpretation. Let me say this for one time. This x here is not just coordinate. It's really the radius of rotation. Remember that part, right? X is the radius of rotation, and f of x is the height of this shell. All right? That's how you remember this formula. Not just x coordinate there, f of x there. F of x is the height of a shell, and x here is the radius of the rotation. So that when they tweak this problem, you don't get confused by coordinates, but you go by this geometric information. This is the amount of radius of rotation, and that's actually the shell. Then you can kind of tweak this formula, but this is fundamental formula. So what was it? Yeah. Okay? All right. Here's a 2 pi x, the circumference of the bottom of the shell, f of x the height. That's one way to remember. And we're still integrating area of something, just like the cross section. But if you overview this thing again, it's very different. There will be a problem in the test that use a cylindrical shell, use washer method, and some problem says do whatever you want. In that case, you have to make the decision, right? So suppose it's that case. You could do cross-section, washer, the disc method, or cylindrical shell. And you have to make the decision. I hope you understand this one. Cylindrical shell is probably the best way to do it. Okay, so here is a picture. If you're doing all the other method, and here's the rotation about y-axis, right, of this region, and the function is a sine of x squared inside, not outside, right? It's not clear about this one. So if you're doing cross-section method, therefore is a disk and washer, this is axis of rotation, and your line segment is a perpendicular, right? So you go from here to there like this. Is that right? Then this part's easy. They gave you this coordinate. Well, how about this one? Do you want y coordinate of that or x coordinate of that if you're doing cross-section like this perpendicular line segment? Which one is it? Do you want the x coordinate of this one or y coordinate of this one? Because it's, distance, radius for this is axis of rotation, radius of this one, from here to there, you want x coordinate, right? From here to there, that's washer method, that you want x coordinate. So you want to solve this one for x. This is y equals sine x squared. And you have to solve this one for x. How does that go? You have to go x squared is the sine inverse of y. So already nervous, I don't know this antiderivative of sine inverse of y, and then you have to put the square root, right? And then this is going to appear after you square it, sine inverse of y. Do I know the antiderivative of sine inverse y? Then you get stuck, right? But if you do the shell method, turns out integral is a lot easier. So we're doing shell method. Okay, so they already gave this to arbitrary position at x. Here's the axis of rotation, and you sketch this line that is parallel to axis of rotation. What do we do with this one? You rotate it around, right? You rotate it around and you're going to get this shell. And there is this PQ right here. Does this reference point PQ helps you to understand what happened? If you just rotate that segment around this, and there's the y-axis there, right? So what was the formula for this rotation around it from, and so given x, we're doing this one, so it is supposed to be integral from x. This is actually the part that confuses a lot. Is it going to be y integral or is it going to be x integral? But if it's a shell method, it's a parallel like this. Given x, we're playing with these two coordinate p and q, so given part dominates the variable. So it's from x going from 0 to root pi over 2. Actually, students pay less attention to this part, but it is actually the fragile part in the test. So pay special attention to which variable am I integrating if it is this situation. All right? Given that, what was that area of? Side of the shell, right? Here, the area of the side of the shell. What do we need to know? 2 pi r, right? The radius. But here, this is axis of rotation. That's exactly the radius. So here's a 2 pi x. That's the circumference in the bottom part. Is that okay? What is the height? Height is exactly this one in here, PQ, correct? So what is that? That's exactly f of x from the x-axis to the top coordinate. So that's going to be sine of x squared dx. That's the formulation. All right. So next part is how to integrate this one. Antiderivative of sine x squared is not easy. I don't know. And as far as I know, it is not elementary. It's not something you can write it down. But there's x out there. That's pretty nice. So the only technique that you learn to computing the integral that is not immediate antiderivative of something, what was that? The only technique we learned so far is the substitution rule, right? So let's think about it. Yeah, it's back again. What is your u make this whole thing easier to integrate? Anybody? X squared, that's right. Why is that? Because this derivative 2x is out there, 2x out there, right? Pretty nice. So let's make this one exercise with this x squared and compute this definite integral. That's your exercise, all right? Exercise number 1 today, compute the integral. Alright, was that okay? Substitution rule? 2x cancel, it gives you only sine u, and pi is a constant, you can pull that out. So integral from 0 to pi over 2, because you're squaring it here, change the limit to the u value, and you have to stick it in there as pi over 2, and this is a really simple number to calculate. I think it's just pi. The answer is just pi. Okay? Alright. So again, do not try to remember this is 2 pi x f of x. And it is a 2 pi times the radius times the height. 2 pi times the radius of rotation times the height of a shell. Then you'll be able to deal with tweaks of the problems. So here's a problem that I want you to do on your own, but let's at least copy this formula in here. Exercise number 2. They're saying y equals x minus x squared and y equals 0. So they're bounding the region with y equals 0, so that's our typical case. But I guess we can look at the tweak here. So this is exactly the same setting as we did before. Alright? And I'm going to show you the formula up there. Let me y equals x minus x squared, and between 0 and 1, rotating around. So you're actually seeing the shape of the thing is not very important. You're analyzing it. Is that going to be, where's this PQ? It's vertical, parallel, stuff from there. How was it? Did it make sense? Alright, axis of rotation, and go to the distance, and that's the radius. Okay, so if there's no question, but always pay attention to, don't stop it here when you practice tonight for the test. Make sure you go all the way to think about how to actually finish off the integral business, right? Some things are tricky, All right, so I'm just going to go directly to axis of rotation around x-axis and see if we can actually handle this. I'm going to make that as an exercise as well. It's a bit challenge, disoriented, but it's the same axis of rotation, and put your line segment PQ parallel to the axis of rotation. Actually rotate it and draw that picture of a slice of can shell, and think about computing the area of that side. That's going to be integral. Alright? Alright. Was that a bit confusing? Because it's different orientation? Alright, let's start again. So here is the arbitrary position of PQ, and I did this in my mind. Q and P always the same formula, so I don't have to draw a second one. If it is actually have to split it up, probably have to sketch the two different PQs, so you have to split up the integral. But here, P always use the same formula, Q always use the same formula, so I didn't do that. So the key thing that you have to remember is that I think it's the same for shell method and the cross-section method. Once you sketch this line segment, you project it down, and that's the variable that you're integrating. You project it down, you land on the y-axis, that is it's going to be y integral. It's the same in the cross-section. You sketch the perpendicular line to that cross-section, you project it down, you land on the x-axis, so your integral is going to be x integral. That's a really quick way to determine which variable you're supposed to integrate. Alright? So it's going to be y integral, so inside everything here is supposed to be y. And I sketch this rotation shell like this. All you have to figure out is height and the radius. And when you do this height, because it's horizontal, you want x coordinate. Length of horizontal, you want x coordinate. Length of vertical, you want y coordinates. So you want x coordinate of this, you want x coordinate of that to calculate PQ. X coordinate here is always 4. X coordinate there, you use this formula to rewrite it, x equals y squared. So distance in between is a right x-coordinate 4 minus left x-coordinate y squared. So that's 4 minus y squared. Radius here, if you think about, here's a line segment, what is the distance from here to there? That's exactly the y-coordinate. That is your main parameter. So it was 0 to y, so it's y. Before it was 2 pi x, and here is 2 pi y because of that. Does that make sense? So 2 pi y times the height of this shell and 0 to b, whatever that y-coordinate there is. So I looked at it here and figured out y-coordinate should be 4. Plug it into this formula. Here was here. Y-coordinate is 2. Therefore, it's 0 to 2. That's the formulation. Is that all right? One more? All right, great. Yeah, let's do one more. Let me just stare at this one for us. You see that if you put the horizontal to the axis of rotation, there are two different integrals you have to go through. You see that a bottom line segment uses one formula, and according to the top parallel line, it's a slightly different formula. You want to do that? Let's try this one. Okay. Exercise number 4. Trying this one. This time, probably have to sketch the 2 segment PQ, because if you move it along, then you realize that uses slightly different formulas for P and Q. All right, how is it? At least sketching these 2 different shells like that and identifying the length. Was there any question about? Bottom here uses this formula Q1. So x coordinate is, if you solve for x, y minus 2 divided by 2. Left hand x coordinate is 0, so that's always y minus 2 divided by 2. Okay? And what else? The radius at this part here, this is axis of rotation, so from here to there, that's always y, and that's always y. And top there, the height of the shell in here, which is this distance, never changes as y going up and down. Always a 2 and always 0 on left hand. So it's 2 minus 0, it's always 2. This actually never changes except the radius. So these are the 2 things. So how are you going to integrate? Y going from where to where to handle the first case in the bottom? What is the bottom value of the first integral for P1 and Q1, that shape? We don't start from 0, I think. Actually start from 1. It has to be y value. Is a given y value. We're integrating with respect to y. That's a key part. So y starts at 1, right? That's the bottom, beginning of the region. So go up to where? Whatever that point here is, which I didn't find. So whatever, if that's a b, so I'm going to go first down. Okay, 1 to b, we're going to use this shell shape here, right? So 2 pi, what is the radius of rotation for that first shell? Y, right? Look at it here, radius of rotation is y. What is the height of rotation? This is y divided by 2 divided by 2. Is that right? Yes. Apologize about this. For some reason I put 1. That is incorrect. That is 2, because that number, if you plug in here, is a 2. Thank you. Correction. Here's a 2. The tick mark is by 2. So it seems like it's 4, but you probably have to calculate it. So that's actually 4. Suppose, well, we'll do that later. Thank you for the correction. But that's the first part, right? All right. And the second part, going from y equals b2 all the way to 8, it's marked in here, y equals 8, and the radius is same, the 2 pi y, times the height is always 2 and dy. And to find b, it's this intersection of y equals 2x plus 2 and that intersection with this vertical line x equals 2. So that's why it's 6, right? There's a 6, yes, right. So y equals 6. So b becomes 6. So it's 2, 4, 6 as indicated in the picture. So that really becomes 6 there. So integral of this polynomial part's easy, so I'll leave it there. Was it alright? Okay. So that's that. Using a cylindrical method to this rotation is not a good idea, because if you do washer method, your segment is going to be vertical, right? If you put the vertical here, that's just all one formula. You see that P is using always one formula, and Q is using always one formula. So the best way to integrate this one is not cylindrical method, but washer method, right? So it's going to be a lot easier. You don't have to do just two integral, just one integral. Okay? The comment make sense? Yeah. It's not going to be exercise. We're going to do this together. Different axis of revolution. All right? So use either washer method or shell method to find the volume of solid that is generated when the region is in the first quadrant, bounded by this two curve. Three things: y equals x squared, y equals 4, and x equals 0, revolved about following lines. But we're going to use cylindrical method. We're going to stick to the cylindrical method today. So let me sketch that first. First quadrant look like this. Y equals x squared look like this. X equals 0 is here, and y equals 4 is there. So the region they're talking about, this one, right? Okay. So y equals -2 is, I think is 2 is somewhere down here. Let me use the red line. Y equals -2 is somewhere down here, right? That is of our axis of our rotation. We are rotating about this line, not about x-axis. But use the same principle in x-axis, just slightly, push it down. So here's this region right there. We're rotating about this one in here. Two ways to do this. You were bothered by this off location. You can shift everything upward by 2 units. Then you enter exactly the same x-axis rotation, and the distance between this region and this axis of rotation is kept as we shift everything upward by 2 units, right? And or you can just do it in this way. And the latter one that I'm going to try to attempt in here. If I use the shell method, and you're going to sketch this horizontal line that's parallel to this axis of rotation, so that's your P, that is your Q, correct? Do you see you have to separate it, or is this going to be all the same formula for P and Q? Do you see the need for drawing another segment, or is this okay? Q always use the same formula, right? And P is always 0 in x coordinate there, so that's going to be it. So if you rotate this one, then you're going to get PQ here, rotate around like that, right? And what is this line in here? That's what you have to be careful. What is this line? Y equals -2. That's the axis of rotation, right? Y equals -2. And this is the y coordinate y there. Y is y. That's the given y value there. That's the coordinate, not the radius rotation. And the coordinate of axis of rotation, there's y equals -2. Okay, so let's first compute this one. What is the height of this shell, which is this length in here? X coordinate there is y equals x squared given y. So what is the x coordinate there? Root y. If it's over to the other side, it's negative root y, right? But you know it's in the first quadrant, it's a positive root y. And what about this one, x coordinate here? It's 0. So given y, what is the distance between that? It's a root y minus 0, right? X coordinate. So that's the height. How about the radius in here? That's the thing you have to be careful. Radius r here is top y coordinate minus the bottom y coordinate. What do you think? That's the distance between the two y coordinates. Make sense? Top y coordinate minus bottom y coordinate. So it's y plus 2. And that makes sense. Here's y coordinate, go another 2 units down. So y plus 4 makes perfect sense. But you can do mechanically like that. Top coordinate minus the bottom coordinate always gives you a positive number, y plus 4. Make sense? All right, let's write down area, right? Area of the side of the shell. So V is the volume going from where to where, y value? It is about what kind of line segment you're covering in here. So what is the y value at the beginning? What is the first line segment shows up? PQ. So right here, right? Right above that, that's the region. So y should start from 0, not from -2. Just like the earlier one that I did wrong. Not 1, but 2. But point is not 0, right? And go all the way to where? All the way to the last segment, 4. So how is this area of the side of the shell? 2 pi, right? The radius, circumference. What is the radius here? Radius of this shell, bottom radius. Y plus 4? See that? That was the radius of rotation there. What's the height of the shell? Is the height of the shell here, right? Root y. So I think the key thing is that if you like to juggle things in your head, that's fine. But if you sketch the shell and write things down, that really helps you to, when you write this formulation down, integral formulation, you convince yourself, I'm doing things right. Or I'm guessing at some point, and then you might make mistakes. So I think this picture and identifying this thing is a key thing. And don't just go by coordinate, but go by distance, and then you not get confused by different axis of rotations. Yes, go ahead, Abigail. That again. Before, axis of rotation was always at x equals 0 or y equals 0. This time, axis of rotation is down here, y equals -2. So the distance from here to that one is rotated around it like this. So radius of rotation is from axis of rotation. Before I just wrote y equals 0 or just y. This time specified as here. Axis of rotation in here is y equals -2. And top part here is always a y coordinate. No matter what the situation is, the y coordinate of that one is written there. Difference between these two is the top y coordinate minus the bottom y coordinate. That's what is calculated here. Yeah, it is really common mistake, and this is one of the part that not everybody gets it. So that's why I ask you to memorize the formula, not in terms of coordinates, but in terms of relative information. 2 pi radius times height, and you actually calculate those radius carefully, not just writing down coordinate. Hey, x goes there, y coordinate. Sometimes it's y plus 4, like this. All right? Does that make sense? So I think writing down this axis of rotation specifically like that might trigger you think carefully when you practice today. All right? And here's more. Time's up. I